All right, what's going on, everybody? Today we're going to be doing another LeetCode problem. This one's called generate parentheses. We'll be solving it in C++ as always. So let's get into the problem. We're given in pairs of parentheses, and they want us to write a function to generate all possible combinations of well-formed parentheses given in pairs. So we're just given an integer n, and basically let's look at this input-output example. So this first one, so when n is 3, that means we need to generate all possible combinations of well-formed parentheses where there are n times 2 parentheses total, or n times, right, n times 2 parentheses total. So for n equals 3, it would be 6 total parentheses, 3 open parentheses, 3 closed parentheses. So, and that's going to be the same for each string in this result vector. And by well-formed, you can see that each of these strings of parentheses have a valid order in terms of arithmetic or in terms of like writing code. So like an invalid string of parentheses would be like, for example, like this, because for one, you can't have any closed parentheses if you're not closing an open parenthesis. Like every closed parenthesis has to be closing an open parenthesis. And then likewise, this open parenthesis here is never closed, so it's invalid. So that's what they mean by well-formed. It has to be like, it would have to work in like a mathematical expression or in like a coding expression or something like of that nature. So basically, to get into this, to get into the code here, well, I'll actually explain the algorithm first a little bit, but we're gonna use recursion. So we're gonna use recursion, and I'll explain the algorithm here, and then we'll talk about the time complexity. So let's just go through this whole algorithm. So for recursive problems, you typically have like a decision tree. So we're going to say our input is n equals 2, and then go down this decision tree. So basically, we're just going to start with an empty string, and we want to go from this empty string. We want to keep branching from this empty string until we have basically all of our desired combinations as leaf nodes of this decision tree. So leaf nodes meaning like the end of a branch. So let's branch, and we're gonna have, there's gonna be two possible ways we can branch for our algorithm, and I'll explain that here. So let's get this set up like this. Perfect. So for the first, basically the first thing we're gonna do, the reason why there's two branches, basically long story short, is you're either gonna be adding a open parenthesis or a closed parenthesis at each step, basically. So those are like the two ways you can branch off here. So, but there's rules. You can't just add them all the time, right? Because they need to be well-formed combinations. So the rule for adding open parentheses is you can always do that when the number of open parentheses in your string is currently less than n. So as we can see, there are 0 open parentheses, so we can definitely add one. So we will add one there, and then let me try to space this out a little bit because this tree might get kind of big. For this side, the rule for adding closed parentheses is the number of closed parentheses needs to be currently less than the number of open parentheses, because every open parenthesis needs to be closed. So let me just like write those rules actually. So I hate how it adds those periods. I gotta get rid of them. This one and this one. So add open while less than n, and then we add closed while closed less than open. So those are the two rules for our two different branching options. So we're basically going to follow that same logic all the way down the tree. So let's branch here again. I'll put this, let's see, try to space it out as much as we can here. So the next step of the branch is going to be, can we add an open parenthesis? Yes, because there's we haven't reached 2 yet. There was only 1, so that side of the branch is good. Oh, also this side we can't add. I don't even think I said this. So for this side, obviously we can't add a closed parenthesis, because if we're looking at this rule, like there are no parentheses to close here. So this is just going to be a dead end. And the way this is going to work is we're going to have if statements that will prevent us from ever calling recursively this direction. So I'm just going to put an X to denote that we're not going to go that direction. And then I can space this out even more. So, but on this side, notice how we do have one open parenthesis, but no closed parenthesis yet. So we can add a closed parenthesis at this point of the tree. So let's do that. And then we're going to keep branching. So bear with me here as I work on my ASCII art skills. There we go. And there we go. Probably want those a little more spread out, because this is going to start getting pretty tight here. But nevertheless, so for this side, notice how we have already reached 2 open parentheses. So we cannot branch that way anymore. So that's going to be a dead end. But we can keep going this way. We can add a closed parenthesis, because notice how the number of closed parentheses is still less than the number of open parentheses. So parentheses, sorry. Yeah, so there we go. So we can do that there. And this is we're gonna just run out of space here. But for this one, we can add an open parenthesis because there's only 1 and we need 2 still. So this string is going to turn into that. And then I'm going to space this out a little bit this way. And then we can not add a closed parenthesis here because because this isn't true. There's an equal number of open and closed parentheses, so we cannot add a closed one. So I will denote that with an X, dead end. Okay, so now we're getting there, almost there now. So let's see. I'm gonna actually try to space that out a little more. There we go. Okay, and then I'll put this over here. This is coming from this node. Hopefully that's clear. I'm just trying to space things out a little bit as much as I can. So next here we cannot add any more open parentheses, so this is actually a dead end. And then this is going to be, we can add a closed parenthesis because there's 2 open and only 1 closed. So we get that. And then for this side of for this node, we cannot add any more open parentheses because there's already 2. And but we can add another closed parenthesis because the number of closed are still less than the number of open. So, and pretty much that's just about going to complete the algorithm. Obviously, we'd look again at these and then notice that the number of closed parentheses is equal to 2. So that would indicate we have a complete, well-formed string of parentheses here. Likewise for this one. There's multiple ways you can check if we've got a final string here. One way being, like I just said, if the number of closed parentheses equals 2, that's one way to check. Another way is if the length of that string equals n times 2. That's another way. But nevertheless, this is what the decision tree looks like for the entire recursive call stack for n equals 2. And we can actually see from that decision tree that the time complexity is going to be big O of time. The time, I'll just say time for time complexity is going to be 2 raised to the 2n. You might be like, if you've never seen big O notation that looks like this, there can be coefficients here in the exponent. Those are actually important for big O notation. It's not like coefficients in the base where they just go away. But nevertheless, it's going to be 2 to the raised to the 2 to the n, because this 2 to the n corresponds to the length of each well-formed string of parentheses, which also corresponds to how many steps it takes to create it. And the 2 here on the base corresponds to, there's 2 different branches at each node in the decision tree. So that's why the time complexity is the way that it is. But that's pretty much it for introduction. We can get into the code now. So the first thing I'm going to do is we're going to need a generator function. So I'm going to implement that as a private function member here for our class solution. And we don't need it to return anything. I'll just call it gen for short for generator. And it's going to need some parameters. In C++, it's best practice to pass parameters in explicitly with each recursive call. It's not good practice to use global variables when you're doing recursion. So just a FYI there. So that's why we're passing so many things around. So nevertheless, it's going to take, let's see, the first argument is we want the current string, right? So we'll just call that cur. We also want to keep track of the count of open parentheses, so we'll just call that open, and then keep track of the count of closed parentheses, so we'll call that closed. And you might be thinking like, well, we could just count, in the string. Well, that's going to like destroy our time complexity, so let's just pass those in as parameters. Int in for the for the input that they gave us, and then also we need a vector of strings for our result, and we want to pass that by reference because we don't want to keep reallocating space for our result array. That's kind of a a global variable, so to speak, because we want to return that answer, and we want the answer to be the same across the entire recursive call stack, that final answer, the final vector of strings. So that's pretty much going to be the function signature. Now let's seed it in our solution function. So we're going to have a vector of integer, or a vector of strings for the result, and then we can seed that generator function. And when I say seed, I just mean like call it for the first time. So it would just be like this. It would be this part of the tree, the root, I guess. But yeah, nevertheless, so we're going to call this generator function. It's going to be an empty string at first. Obviously, the number of open parentheses is going to be 0, and the number of closed is going to be 0 also at first, because it's just an empty string. And then we pass in n, and we also pass in res, which is by reference. And then we can just return the results after that. And this will execute the whole recursive call stack chronologically, so you don't have to like do any weird like async stuff or anything like that. You can just call return res immediately after. So let's get into the function implementation for the recursion. So this is the good stuff here. So the first thing we can do is basically check if we have a completed string like these. So if we're at like a leaf node, that's the first thing we want to check. So if, and then remember I was talking about a few ways you can check that. The way I'll do that is we'll just ask if closed is equal to n, at which point we can push back the current string to our result vector, and then we can just return from this branch of recursion. So that's for leaf nodes. Now we need to see what to do if we're not at a leaf node, if we're at like one of these nodes. And then there's going to be two if statements, right? Because one of them adds the open parentheses, and then the other one adds the closed parentheses. So and then remember what our rules are. So we're only adding open parentheses while the number of open parentheses is less than n. So we can basically just say, while if open is less than n, then we can add an open parenthesis. And the way we do that is we'll just call our recursive function again. And remember, we're adding an open parenthesis here. So it'll look like that. And then we need to increment that count of open parenthesis for the next function execution, the next execution of that function going down that path. So open +1, closed is going to stay the same, and is always going to stay the same, and then res is always going to stay the same. And then we're basically going to do something like really similar for this when it's time to add close parentheses. So we'll add a close parenthesis, and then open stays the same and closed gets incremented. And then the condition here is you only add closed parentheses while there are less closed parentheses in the string currently than open parentheses. So while closed is less than open, you add closed parentheses. And that's pretty much going to do it for the code. There's really not that much code. So let's go ahead and run this and see if there's any bugs in there. Does it? Yeah, so it passed those. So let's go ahead and submit to look at our percentages. And beats 49% with runtime, 44% with memory. So decent, I might run it again, see if we can get a little higher. But yeah, nevertheless, this is one way to do this problem with recursion. So hopefully this helped you understand this problem more. If it did, please leave a like and subscribe. It helps the channel grow. So appreciate you guys for checking out the video, and thanks. See you guys in the next.